Hey everyone, and welcome to today's explainer. If you're a focused learner trying to really truly grasp the foundational pillars of data structures and algorithms, well, you are in the exact right place. Today, we're not just going to sit here and memorize code. No way. We're going to visually break down exactly how memory behaves, how multidimensional grids are actually manipulated, and the hidden mechanics of text strings. So grab your mental notepad because we're about to build your engineering intuition totally from the ground up. Here is our quick roadmap for today. First up, memory and loops. Second, transforming 2D matrices. Third, string logic and immutability. And finally, we'll wrap things up with some critical interview pitfalls and revision strategies. All right, part 1, memory and nested loops. Let's get right into where our data actually lives, because honestly, you can't write efficient algorithms if you don't know where your variables are hanging out. So think of computer memory as having two main neighborhoods, the stack and the heap. The stack is super organized. It stores your static memory, primitive types like integers and method calls. Think of it literally like a stack of plates at a cafeteria. It operates strictly on a last in, first out, or LIFO basis. You got to take off the top plate to get to the ones underneath, right? Now the heap, on the other hand, is your dynamic storage. That's where objects, arrays, and complex data structures go when they need flexible memory allocation. When you create a new array, the actual data goes to the heap, but the reference pointing to it, that stays safely on the stack. Okay, so now that we know where our data lives, how do we traverse it? Well, a nested loop is exactly what it sounds like. It's simply a loop executing inside the body of another loop. And it's an incredibly powerful tool, especially for multidimensional structures like 2D matrices. But I really want to give you a warning right now. Nested loops require very careful complexity analysis. They are an absolute double-edged sword when it comes to performance. Look at how this works in action. Notice how the outer I loop takes just one single step. And while it just sits there, the J inner loop has to complete its entire cycle, from start to finish. Only when J is completely done does I increment to its next step. And then, J has to start all over again. And this right here is exactly why time complexity is so crucial. Because that inner loop runs n times. For every single one of the n outer steps, you multiply them. N times n gives you n squared operations. This is quadratic time, or O of n squared. While O of n linear time grows smoothly as your data increases, O of n squared grows exponentially steeper. To put that into perspective, if your input size goes from 10 to 100, your operations don't just multiply by 10, they multiply by 100. It's the exact kind of math that quietly crashes production systems if you aren't paying close attention. Moving right along to part 2, transforming 2D matrices visually. Let's take what we just learned about nested loops and apply it to mathematical grids. Picture this. You're in a whiteboard interview, and the universal panic sets in because a 2D matrix question just popped up. It's a classic scenario. How do you efficiently rotate an entire matrix by 90 degrees clockwise? Imagine it's an image grid you need to rotate on your phone. You can't just brute force guess where the pixels go, right? You need a structured, mathematical approach. Turns out, we can break down this seemingly complex rotation into two crystal clear, totally actionable steps. Step 1, transpose the matrix, which basically means swapping its rows and columns. And step 2, simply reverse each row individually. Let's look at exactly what this means visually. This brilliantly illustrates that first step, the transpose. We identify the principal diagonal. That's that line of elements running from the top left straight down to the bottom right. The elements along this diagonal stay exactly where they are, but every other element, they swap places across that line. The element at row I, column J, perfectly swaps with the element at row J, column I. And now for step 2. We take that newly transposed matrix and we just reverse the elements in every single row. Notice how, as the rows reverse, the entire grid suddenly just magically aligns into a perfect 90-degree clockwise rotation. We just solved a really complex 2D spatial problem with two super straightforward linear algorithmic steps. Okay, quick checkpoint recap to lock this in your brain. 2D matrices are n by m grids. Transposing a matrix means swapping the I and j indices across the diagonal. And a 90-degree rotation? It's simply a transpose followed by a row reversal. Memorize that little formula and you will literally never struggle with matrix rotation again. All right, part 3, string logic and immutability. Let's talk about strings, which are honestly just sequences of characters. but they harbor a very crucial, almost hidden memory secret. The contrast in memory allocation here is actually fascinating. When you create a string literal using double quotes like scalar, the system efficiently stores it in a shared area of the heap called the string constant pool. If you make another string with the exact same text, it just lazily points to the existing one. But if you explicitly use the new string keyword, you force the system to allocate fresh, separate memory space outside the pool on the heap, even if that exact text already exists. And this brings us to a massive secret that interviewers absolutely love to test you on. Strings are immutable. Once a string is created, its value cannot be changed, period. So if you try to concatenate or add to a string inside a loop, you aren't actually modifying the original string, you're creating a brand new object every single time. It quietly eats up your memory until your program just crashes. To prevent this, always use a string builder class. It's specifically designed to be modified without spawning endless new objects. Let's put this string logic to the test with a fun little challenge. How do we reverse the words in a sentence while keeping the actual letters inside those words completely intact? For example, turning the string scalar is best into best is scalar. The logic here is beautifully simple. First, we split the original string by its spaces, which turns it into an array of individual words. Second, we iterate through that word array backwards, starting all the way from the last word. And third, we join those words back together, inserting a single space between them. So how do we actually write this out efficiently in Java or Python? Well, we initialize a string array using the built-in split function on the spaces. Then we set up our loop to run backward. But here's the real trick. Inside the loop, we absolutely do not use standard string concatenation. Instead, we use stringbuilder.append for each word. Finally, we convert it back with a simple .toString. This keeps our memory footprint incredibly light. Quick checkpoint. Strings are immutable objects. The string pool optimizes memory for string literals, but you gotta be careful. In dynamic situations, especially loops, using a string builder is absolutely your primary defense against memory overflow and performance crashes. Finally, part 4. Interview pitfalls and revision. Because knowing the code is really only half the battle, right? Avoiding common traps and practicing effectively is the rest of it. Okay, warning time. Here is a major interview pitfall I see all the time. Candidates see a nested loop and immediately shout O of n squared. But hold your horses. Not every nested loop is quadratic. It depends entirely on how many times the inner loop actually runs. If the inner loop only executes a fixed, small number of times regardless of n, or if the step increments multiply instead of adding, your complexity might be completely different. You always have to carefully count the actual loop executions. Don't just guess. Before we wrap up, I've got some actual homework for you, based on the best practices from our source material to really lock in these skills. First, track your participation streak. Consistency is just like going to the gym. You build coding muscle over time. Second, practice writing algorithms on actual paper. This prepares you for whiteboard interviews without relying on the crutch of an IDE. And third, join peer study groups. Explaining a concept like matrix transposition to someone else is hands down the fastest way to truly master it yourself. Putting in this focused effort will totally transform how you code, I promise. We have covered so much ground today. You've traversed the stack and the heap. You've rotated multidimensional grids, and you've safely manipulated immutable strings. You now have these foundational masterclass tools right in your mental toolkit. Keep practicing, keep analyzing your complexity. So the only question left for you is, what complex software engineering problem are you going to optimize next?